Hello, and oh yeah, it's a midterm review. Yeah, no one is gonna get it. We're not getting excited today at all. It's midterm review, so yeah, no excitement here, just high. And let's see what we can do with this review. I received a couple of emails with a couple of problems, which is great. I will pull those up and see what else we can find along the way. I'm trying to get as many problems as possible in, so we can discuss this. Now, before we start with the review, the exam, I'm trying to see if I can have the exam in Canvas. That way we don't have to worry about MyMatlab being, issues with interrupted connections and all of that kind of stuff. So I'm trying to get the exam into Canvas. That way you can log on to Canvas, start exam, and then when it ends right after the time, and then you are done that way. That should be much quicker. Now it's still going to be the same MyMatlab problems, but it's not going to be in MyMatlab. It's going to be in Canvas, so it's so we don't have interruption of service. That's the biggest thing. Again, I'm trying to work all of that out. I know that few of my colleagues managed to get it. I'm not sure if, obviously not for differential equations, for, other courses that are well developed, right? But our course is the first time MyMatlab and so on, so I'm just hoping not to have any issues because it's brand new. So let's... Please make sure you are constantly reading announcements so that you know where the exam is. And I was hoping to have it on Friday to Saturday, so in 2 days, so that we can push on and deal with other 4 chapters that we didn't even touch yet. Especially chapters 5, chapters 7, they're very important, and then whatever else we can get to, that will be right. We did lose a week for the spring break, so hopefully having 3 classes a week is going to make up some time, because as I said, this elementary course is the one that you really need to know to operate on any level, once you transfer out. So let's take a look. I am in the process of getting the email. Just a second. Let's see. It's just 5,000 emails. It's very difficult to even find stuff here because it's just so much. All right, so let's first talk about the midterm and what it's there. So we can do shorter exam with less time, or longer exam with more time. The scoop is that you won't have time either way. You won't have time to look stuff up and rummage through your notes and try to find similar examples and things like that, because right when you are doing that, you are wasting time looking rather than solving the problem. There is a time allocation per problem, and it's not that you can sit there 7 hours and grind an exam that is supposed to be done in an hour. So the idea is to get the questions answered right as quickly as you can, and I generally, whatever MyMatlab says, I leave a little bit more time for checking and all of that stuff. So if the MyMatlab says that it should take you 40 minutes to do something, I leave an hour. If it says that it should be hour and a half, I leave 2 hours, and so on. I always add extra 30% or whatever time, 25-30% extra time, so you have enough time to also check. And sometimes you need to think about things. So it's either going to be 8 or 10 questions, maybe 10. Right, it's a midterm. I was thinking maybe 10 for 2 hours, but we'll see. So 8 to 10 questions. $130 to 2 hours time, and I'm hoping for it to be on Canvas. Right, so that's our to be on Canvas. I will try to have it there. That will be amazing. I still have 5,000 emails to get to. If you emailed me with whatever concerns or whatever, I will be clearing that out. It's just I had way too much work with all of this stuff. Plus the kids are home 24/7, so there is homeschooling for them, and it's just this quarantine is more a problem than what it actually brings to the table. At this point, it's becoming really, really annoying to operate on every level. So we have to go through topics. So we have, well, first, before I write topics, exam is on chapters 1, 2. So chapters 1, 2, and 3. So those are the chapters. And now let's take a look at topics. So first topic is classification of diffuse, right? So is it a linear, is it first order, is it homogeneous, and all of that stuff that is just classification. So you literally just say, okay, this one is linear, or this one is second order or third order, and so on. So that's classification. After classification, right, definition of ODE, right, of diffuse. That is, what we have. So, and then we said the differential equation is a collection of independent or equation that contains independent variable function and its derivatives. So that's a definition. Basic modeling. That's word problems, right? On a first day, we translated that population problem. Later on, we had a little bit trickier population problems. And then we had the spring mass and the electrical circuits and all of that kind of stuff. So it's getting more involved as you go through. But, we also have acceleration and velocity. Basic modeling means you are taking some simple case, right, and writing a simple differential equation, and most of them are solvable either by basic chapter 3 stuff or separation of variables or something like that. So you have Newton's law of cooling, you have population stuff, acceleration, right? So pretty much straightforward. All right, then we have slope curves. So that's those graphs with lots of little slopes that guide the solutions through the space, right? So you first calculate those isoclines, and then you draw little slopes on each isocline, and then you snake the solutions through. Then we have separable equations. That one should not need any explanation. Then we have substitution. Again, something that it's not taking 10 years to solve. And finally, exact equations. exact equations, which is conditions plus solution. So you have, right, those conditions to figure out whether the equation is, right, exact and so on. And that this is all in chapter 1. Now in chapter 2, we have our population models. Well, that's under basic modeling up there. So nothing crazy there. Equilibrium and solutions and stability. I said we're just going to skip that one on the test. Acceleration, velocity models and numerics. Wow. So I don't get to put much from. So let's write it. Population, and you have the basic plus logistic model. Then you have your velocity plus acceleration, and then we have numerics, and that would be 2.4 through 2.6. Now we were supposed to have this exam in class. You were supposed to memorize the formula for Euler, and then if any others show up, I will give you the formula. So, you know, now you just, I guess, you'll just have the formula. So we just plow through calculation. I can't really police that, but it will come back to haunt you later if you don't know it. I mean, that's always how it goes in math. You probably experienced that by now. The next is the chapter 3 stuff. So we have the constant so second order ODE. ODE is ordinary differential equation, right? Because you have partial differential equations, this is more stuff. This is, as I said, this is not covering even the fraction of 1% of what's out there. The whole course is covering a fraction of 1% of the stuff that it's out there for differential equations. So ODE stands for ordinary differential equation. So second order ODE with constant coefficients, and that's the one that has the three solutions, R1, R2, R1 equal R2 equal R, which is repeated and then complex, right? So those are the 3, 1 and 3, 3. Then we have higher order, we can factor, and when we factor it goes again into these. Then we have word problems, which are mechanical vibrations. Those are the basic problems. Mechanical vibration, homogeneous case, right? So those are the easy ones, which is just you use R and you get the solution. And then we have the non-homogeneous equations, right, which are giving us either undetermined coefficients or variation of parameters. And then we have the word problem for those, which are called forced oscillations. Plus circuits. Those are the two sections we did in one shot. And that's it. That's the midterm. That is supposed to be the half of the course, right? This midterm was supposed to technically be done, you know, the day after the spring break, so 3 weeks ago. We are now going to look at the problems. Again, trying to find the problems that are not taking too long, right? So we had that one wonderful undetermined coefficients problem, which took a very, very long time, and with your help, right? Because I messed up like 5,000 times. Yeah, nothing like that, but we must have undetermined coefficients with something that it's quicker, right? So if you have a problem that you would like to work on, you have questions for, you can ask in chat here, or I have a couple of emails. I'm doing 2 emails so far that yeah. So that is, yeah. I'm just trying to find the email. Here we go. So a couple of these. Now, also important thing to note that when you are doing and practicing problems on MyMATLAB, if they have a capital letter T, you are expected to use technology, whether it's numerical calculation or if you have to integrate, because remember, we can't integrate everything. Yes, you did have Calc 2, but that doesn't cover all of the situations for integration, right? Those are only basic methods. I mean, calculus and differential equation is labeled as elementary mathematics. I mean, you still have another 20 years of math after that if you're interested in it. So clearly the elementary concepts are not going to cover everything that is available to us. Therefore, we we have to work on, right? Sometimes you have to use software to integrate and go through the problems. So let's take a look at a couple of these email problems. I see the request for population example. Again, the population example, which one? Are we talking about day 1 or we're talking about 2.1? So, try to be a little bit more specific, but sure, we will definitely look at the population as well. So let's see all of the things that I can I'm trying to find some of the problems that would be close to or somewhat important for us. Here is a good one of y to the fifth derivative of y plus 2y, the third derivative, plus 2y double derivative is equal to 8x squared minus 9. So we have to use variation of parameters, the undetermined coefficients for that part, but let's take a look at what we have over here, right? So we gotta do yc, right, first, and yc, and we do that by r to the 5 plus 2r cubed plus 2r squared equal to 0. So that's where we start. We factor out r squared, and we're left with r cubed plus 2r plus 2 equal to 0. So now we have r squared equal to 0 and r cubed plus 2r plus 2 equal to 0. Just trying to verify that this is equal. Okay. Now, why am I doing this? I'm doing this because of duplication. I'm making sure that there is no duplication for any of the terms. And we do see some duplication, which means that we have to go to the higher available power. So let me just see if I can factor this one real quick. So what do I need? I need r cubed plus 2r and then plus 2. So it factors over 1 real and 2 complex. So R equals about 0.77 and another, there's R equals 0 here with multiplicity 2. Then there is this R, and then there are R's that are complex, which are 0.39. We were not supposed to find this. This was not a question. I just want to, do the complete problem. Plus 1.56i. Cool. So we can find our complementary solution here, and we see that we have a repeated root on 0, which is a constant, right? So we will have yc to be c1e to the 0 plus c1xe to the 0, right? So when you are simplifying that, you will just get c1 plus this is c2x, right? Then you need to have plus, this one is supposed to be c3e to the 0.77x, so that one stays as is. And then we have the 2 complex ones, so plus e to the 0.39x, and then we have c4 cosine 1.56x plus c5 sine 1.56x. So that also carries here, and that will be our EC. Even though they did not ask for this, but since have access to technology to factor this nonsense, right? We got it. There we go. Right, so that's YC, and now we need to find YP. So if you are observing over here the pattern, our f of x, right? Our f of x, we have f of x is equal to 8x squared minus 9, right? And we don't have that in our toolbox down there, right? You see that there is a constant term, and there is a constant term, and there is a linear term. So we would like our YP to be ax squared plus bx plus c. But both of these are repetition, right? So I need to bump everywhere by x. So the new yp that I would like is by 1 power higher, but then now this is still repeated. So I need to bump it 1 more power, and finally now there are no repetitions. So you start with what it should be, then what you should like it to be, right? And you keep bumping up powers until you are in clear from YC. This is why I did YC before. I don't think you can do this without solving YC. So now I know that my YP is ax to the 4 plus bx cubed plus cx squared. And this being a wonderful MyMATLAB problem, now I need 5 derivatives of this stuff, right? So I can plug everything in. So let's go. Yp prime is 4ax cubed plus 3bx squared plus 2cx. Yp double prime is 12ax squared plus 6bx plus 2c. Then yp triple prime is 24ax plus 6b, and then 2c, that's a 0. Then the fourth derivative, remember we are now changing the notation, is going to be 24a, and finally the fifth derivative is a big fat 0. Where do you look for repetition? I am looking between the YC and what I have. And I had repetition here, and I had repetition here. Actually, I should have circled. That's a better when you simplify. You have a constant term and you have a linear term, and that's a repetition, so we keep bumping up powers until we are out of repetition. So if you take a look at this one, there is no repetition between the two because you have a constant and you have a linear, and then yp now has a quadratic, cubic, and the fourth power. So that's where we look for repetition. Alright, so now we're supposed to plug all of these in. So plug in a differential equation, which is the fifth derivative plus 2 times y, third derivative, plus 2y, second derivative, equals to 8x squared minus 9. So plug in 0 plus 2 times the third derivative is 24ax plus 6b, plus 2 times the second derivative is 12ax squared plus 6bx plus 2c, and all of that needs to be equal to 8x squared minus 9. So I have 48ax plus 12b plus 24ax squared plus 12bx plus 4c. So one more time, 24 times 2, 48, that's a 12b, that's a 24ax squared, that's a 12bx, and that's 4c equals to 8x squared minus 9. And the x squares, I only have 24a, and that's equal to 8. X equation is 48a plus 12b equals to 0, no x term on this side, and then constant is 12b plus 4c equals negative 9. So from here, I am getting that a is equal to 1/3. So if a is equal to 1/3, then this equation, a third of 8 is 16, right? So I have 16, so 12b equals negative 16, b equals to divided by 4, negative 4/3. And then if b is negative 4/3, then that's negative 16. Well, that's negative 16 plus 4c. Right, all of these are separate lines, right? You have this line, and then you have this line to give you b, and now I'm working on a third equation on the bottom. So when I plug in b, negative 4/3, oh, actually, hold on. You can see that 12b, which is 12b, is negative 16. So you just plug the whole thing in. That's great. All right, cool. So negative 16 plus 4c equals negative 9. That's 4c. 4c is equal to 7. So c is equal to 7 over 4. I hope. And we have our yp to be what? Go up there to yp. So that's a x to the 4th. So that's 1/3 x to the 4th minus 4/3 x cubed plus 7 over 4 x squared. There you go. That's the yp. So that's our yp. Now, if you want, I mean, they're 3, 3, and 4, so we won't have to do the common denominator to pull. It's just whatever. So y is equal to yc plus yp, and we have the yc up there. We have the yp over here is equal to answer, right? It's too long to copy and write everything. Our yc took a whole line. So here is your yc. Right there. So that's gonna go with that. And then here is your yp. And that's the answer, right? So y is equal to yc plus 1p. I mean, this wasn't insanely difficult or long. Being that it's a take-home test, it shouldn't, it shouldn't really bother you. So there are a lot of these problems to work on. Variational parameters, coefficients with trig. Yeah, so when you have trig since we're talking about undetermined coefficients, undetermined coefficients with trig would be using the same idea, except now you are using, a sine plus b cosine as your coefficient. I'm trying to see if I can find anywhere perfect. So I'm gonna write this in blood. Page 191, chart on the top of the page. So this chart is teaching you, looking at f of x, what your yp is, right? And you can see this xs in front is multiplying by x to the s if you're having repetition. So if we have repetition, we use x to the s. If there is no repetition, you're ignoring x to the s. Now, what is x to the s? Well, whatever the next exponent needs to happen, right? Earlier, we bumped it twice, right? We had to bump it twice because it was repeating, right, on the linear, then it was repeating on the, constant, and then it was repeating on the linear, and finally x squared was the first one that wasn't repeating. So, in terms of trig, if you have y to the triple prime plus y prime 2 minus sine x. So this is undetermined coefficients with the trig, and then we'll focus on variational parameters next. So here is your problem. We first deal with the yc because we need to know if there are repetition, right? There is no repetition, but do it because you can. It's r cubed plus r equal to 0. Factor out r squared plus 1. Oh, actually there is repetition. Holy nightmare. R equal to 0. And then r equal to plus minus 1. Holy nightmare. If I didn't do this, it would be, plus minus I. So yc is c1 e to the 0x plus c2 sine x plus c3 cosine x. And now we can just get rid of the e to the 0x. So yc is c1 plus c2 sine x. You can put cosine if you want there, first doesn't matter, plus c3 cosine x. This is our yc. I used the wood paneling before, right, to box it. That's our yc. And now we're going to just gonna answer a quick question. All right, so we have now our yp. I want my yp to be a plus b sine x plus c cosine x. That's what I want it to be, because as I am taking the derivative of sine, sine becomes cosine, cosine becomes sine, sine becomes cosine. Well, there are minus signs floating about, but the idea is that as you're differentiating sine, you keep getting cosine, and when you differentiate cosine, you keep getting sines. So they keep looping. So if you just have sine or cosine, or if you have sine and cosine on a pile, it's always the same setup, right? Now we also have a constant here, So I had to put that one in as well because the derivative of 2 is 0 and that's different than 2, so that would change. So now these are all repetitions. That repeats, that repeats, that repeats, which means that I have to use x's in front. So yp is ax plus bx sine x plus cx cosine x. I'm using that as my yp because of repetition. They're all repeated. You see that there's your a, repeats, constant is constant. Then there is a sine term that repeats and a cosine term that repeats. So I had to bump them all by x to make them non-repeat. So now that I have my yp picked as ax plus bx sine x plus cx cosine x, we now need the derivatives. And for this problem, unfortunately, I need 3 derivatives to plug this in. And these are all, right, product rules here. So these derivatives are going to get really annoying and very long and nasty, but it's differential equation. So we have a plus copy the first derivative of the second plus copy the second times derivative of the first, good, plus copy the first derivative of the second plus copy the second derivative of the first, good. So yp prime is given as a plus, and now we can actually combine like terms. Let's just write it bx cosine x plus b sine x minus cx sine x plus c cosine x. So that's y prime. Now I need y double prime and then y triple prime because I need to plug them in. So yp double prime, the a is just going to be 0, so we don't have to worry about that, plus, and now I have, again, product rule there and a product rule there. The rest ones are just straightforward. So copy the first times derivative of the second plus copy the second derivative of the first plus derivative over here is b cosine x. Now minus, and in the parenthesis here I have copy the first derivative of the second plus copy the second derivative of the first, and then plus, no, minus, derivative of cosine is negative sine, so negative c sine x. See, it's just a lot of mess here. Negative bx sine x plus, these are two the same, so 2b cosine x. Then I have minus cx cosine x. And then I have minus 2c sine x. This minus distributes, so minus and this term is the same, so they add to a single term here. All right, cool. So I got that. I'm just gonna get rid of all these lines that we don't need anymore. All right, cool. So that's a y double prime. Maybe I should. Let me just put the bullet points for all of the lines that I will be actually plugging in, because now we need to sort out the third derivative. You can put 3 tick marks, you can put the 3 in parentheses, I don't care. And I need just one more derivative, and we'll be ready to plug everything in. So we have copy the first derivative of the second plus copy the second derivative of the first. Now minus 2b sine x, because derivative of cosine is negative sine. And then minus copy the first derivative of the second plus copy the second derivative of the first is just a c. And then minus 2c cosine x for the last one. So now we have to clear up this mess. Now that's negative bx cosine x, negative b sine x, negative 2b. Oh, that's a negative 2b sine x, so that's negative 3b sine x right there. Plus cx sine x minus c cosine x and minus 2c cosine x, so that's a minus 3 right there. Cool. And that's our third derivative. So now we need to plug them in. And we are plugging in into third derivative plus the first derivative is equal to 2 minus sine x. So the third derivative is this negative bx cosine x negative 3b sine x plus cx sine x minus 3c cosine x, right, 3c cosine x plus y prime, which is a. So y prime is this bullet point here, plus bx cosine x plus bx cosine x plus b sine x minus cx sine x plus c cosine x equals to 2 minus sine x. There we go. Woohoo! Collect like terms, work out coefficients, and we are done. All right, so let's go in order. I'll start with a is equal to 2 because that's our only constant. Let's write constant. A equals to 2. There are no other constants. Everything else has sines and cosines, right? Then I have to collect all of the sine x terms. Oh, but I also have x sine terms. Do they cancel? Yes. This one and this one cancel. And where are my x cosine terms? Okay, good. Phew. So I have, for sine x, I have negative 3b. What else do I have for sine x? I have a plus b. So negative 3b and a plus b. Well, that's equal to negative 2b, and that's equal to negative 1. So b is a half. And the cosine x is negative 3c plus c is negative 2c, and that's equal to 0, and c is 0. Because there are no cosines on this side for a coefficient. That's why it's equal to 0. So my yp is A plus 1/2, where's my YP? So B survives x sine x, B x sine x, B x sine x. Good. So the solution is yc plus yp. Now, again, the two boxes, I think they're shorter this time. Yc c1, okay, easy. So c1 plus c2 sine. So c1 plus c2 sine x plus c3 cosine x plus, and I'm just going to put, now I know you're going to get triggered, but hey, such is life, x sine x, ignoring this, because it's absorbed in C1. I know it triggers you, but I'll write it. 2 is absorbed by C1. And that should be it. That should be it for one of these with the trig. It's just a lot of writing. It should not be an issue. Now we have variation of parameters. You know, we haven't done any of these problems that have sine and cosine hyperbolic. So let's do one of those. So this is problem 50 on page 196. So y double prime minus 4y is equal to sine hyperbolic 2x. Oh, there is a question, says, isn't the form ax? Hold on, isn't the form ax? It is ax! Holy nightmare! Ah, yp is 2x. You are right. Ah, so this gone. And I have to put in plus 2x over here. Let's see if I do any of the problems correctly today. Yes, you are right. Yp was ax, not just a. So because it was ax, then you have to do 2x, right? So this is your a. And this is your bx sine x. Now I have them in the opposite order, but whatever. It's commutative. Yes, you're right. So, variation of parameters had that formula that you were supposed to learn for the yp. Your yc is not changed at all. You have your r squared minus 4. R equals plus minus 2. So yc is equal to c1e to the 2x plus c2e to the negative 2x. And this is the time for us to pause and reflect. So, who remembers Calc 2? This is equal to 2 cosine hyperbolic 2x. And before you go nuclear, I will write that cosine hyperbolic x is e to the x plus e to the minus x divided by 2. Right now, this is supposed to have some constant as well, so I don't know, big C or something like that, because you can combine these two coefficients and come up with there is a procedure that you can do. Now I just wanted to put that out there because we are still going to use, right, for our Wronskian, we have our y1 c1 e to the 2x, we have our y2 to be c2 e to the negative 2x. We don't need this. I just wanted to put it out there, right? If you are doing variation of parameters, well, that's going to be undetermined coefficients, that's going to be repetition. For variation of parameters, you just plow through those integrals, so we don't have to worry much about it. But right, if you wanted an undetermined coefficients, then you have a repetition and you have to deal with the repetition. So we don't have to do this now, but you know, if it was undetermined coefficients, you would have to. Wronskian. C1 e to the 2x, C2 e to the negative 2x, the derivatives, 2c1 e to the 2x, and negative 2c2 e to the negative 2x. So this is going to be, when you add these, that's e to the 0, which is, right, when you add exponents, they go to 0, so it's e to the 0, so that's 1. So it becomes c negative 2c1 c2, and then minus 2c1 c2 for a total of negative 4c1 c2. Oh, we actually don't need the c's. Yeah, you just use the functions. Don't need the c's. Sorry. I'm just having a terrible day. It's just been since I got up, everything that could go wrong went wrong, and I'm just not focusing at all over here. It's one of those days. So our Wronskian is negative 4. So formula which we memorize for variational parameters is negative y1 integral, and then you have y2 times f of x divided by the Wronskian dx plus, and then you have y2 integral y1 f of x divided by Wronskian dx. So these are the two integrals we have to solve. It's very easy to remember this formula because you are starting with y1 and then you use y2, right? Then you start with y2, you use y1, they look the same, right? Times f of x on top divided by Wronskian on the bottom. First one is negative, second one is positive. I mean, it's so easy to remember this. And we just now need to plug everything in, right? So yp is negative y1, that's negative e to the 2x. And then we have e to the 2x. And then we have sine hyperbolic 2x, right? That's our f of x over here. F of x is sine hyperbolic 2x. Divided by Wronskian, which is negative 4. Plus e to the negative 2x integral, oh wait, this is a negative here, right? That's a y2. And then e to the 2x sine hyperbolic 2x over negative 4 dx. Alright, so make sure you fix this exponent here. It's supposed to be a negative because y2 is e to the minus 2x, the way I did it. And now we need to integrate this mess. Now that's gonna be actually extremely easy. We are going to kick the quarter outside, so we have e to the 2x over 4, negative times negative is positive, integral e to the negative 2x times, and now you write this e to the 2x, right? So you don't have to do integration by parts twice and deal with this. You can just do this and minus e to the minus 2x over 2, and now this becomes basic exponential stuff. Minus e to the negative 2x over 4, because this one jumps outside, right, makes it negative. And you have the same thing as the previous one, e to the 2x, and in parentheses you have e to the 2x minus e to the minus 2x over 2 dx. So you can, okay, let's go. This yp is equal to, now the half goes outside, so it's e to the 2x over 8 integral, and now when you multiply these two you just get 1, because that's e to the 0, minus e to the negative 4x dx, and that's a joke to integrate, minus e to the minus 2x over 8 integral e to the 4x minus 0, sorry, minus 1, and the 2 is kicked outside, dx. There we go. So now we integrate this, e to the 2x over 8. The integral of on 1 is x, minus the integral over here is e to the negative 4x divided by negative 4. So when you're integrating exponentials, they go in, the coefficient over here goes in denominator. That's basic u sub. Minus e to the negative 2x over 8. And we're going to do the same over here. We just get e to the 4x over 4 minus x. There we go. So yp is what? E to the 2x over 8 times x plus e to the negative 4x over positive 4. I combine those negatives. What I'm going to do is I'm going to swap, and that will produce a negative 1. So this becomes a positive e to the negative 2x over 8, and now this is x minus e to the 4x over 4. So when basic algebra formula, a minus b is the same as negative b minus a. So that's how this minus became a plus, because I swapped these two terms in parentheses. And it's just arithmetic, or algebra, whatever you want to call it. Algebra, I guess. So now I multiply all of this. So yp is x e to the 2x over 8 plus e to the negative 2x over 32 plus x e negative 2x over 8 minus e to the 2x over 32. And you can now combine, right, terms over here. So now we'll do some mathematical flexing. X over 4. I'm picking out x over 4 because I want in parentheses to leave with e to the 2x plus e to the negative 2x over 2. Right? And then I have plus, and in the second parenthesis I am kicking out 1 over 16. 1 over 16 is kicked out. And the exponents that are left are e to the negative. Oh, I would have that one as negative, so I have to kick a negative out as well, so that I can have e to the 2x over 2 positive, and then minus e to the negative 2x over 2. All right, I can do it like this, minus there, and single 2 in denominator. All right, cool. So now we're set, because we have a yp is equal to 1/4 x cosine hyperbolic of 2x minus 1 over 16 sine hyperbolic of 2x. And if you look at your problem, right, you see that you had forcing term, right, on the right hand side that made it not homogeneous. Forcing term was a hyperbolic function. You did get two hyperbolic functions in your answer. Now we just went through all of the, simplification. Technically, your problem was done once you integrated, but then, right, we can do so much better than that, right? Combining it into this. So again, y of x is yc plus yp equals 2, and you just, plug them in and you are done. So that was variation of parameters using those two formulas that you remembered, and you go from there. So we still have population problem. We still have, what else you guys talked about? So we did variation, we did this one, we did that one, we did that one. Okay, so there's a population problem. There is as well, there was a problem, I believe was substitution problem somewhere in the email. Kill me now. Mechanical oscillation is going to be this again, right? There is no, it's just oscillations, right? You are going to get constant coefficients second order, and you just plow through the same calculations. So integrating, I forgot integrating factor on the list. See, I knew I forgot something on the list. When you leave the house, you have the feeling that you forgot something. So over here, I'll just put in black, in red, right? Add integrating factor. I forgot about that in chapter 1 somewhere. Was integrating factor. We'll take a look at that example as well. It's been 2 months since we did that, so yeah, good thing you remember. So I hope that is, so what would be given for this type of a problem? I'm thinking, I'm assuming you're asking about mechanical oscillations. So you already know the formula for oscillations. This is going to be very short. You already know the formula for mechanical oscillation, which is mx double prime plus cx prime plus kx equals to some driving force T. You know that formula. So when I give you a problem with the mass and the C and the K, you plug them in, and then it turns into this mindless grind here. And the mindless grind we had before here. And the mindless grind we had before, right? So these 3 problems in a row are your mechanical vibrations, oscillations, and your circuits. It's just that those word problems have an extra step where you plug in numbers from the text because you understand what those numbers mean. You understand the resistance goes for R, C goes into 1 over C, L goes into inductance in Henry's, right, for L, M is the mass, C, right, is the dampening constant, and K is the spring constant. So your job is to fit those. So the word problem here is just an extra step to plug the numbers in where they belong, and then the rest is just a mindless grind, the procedure that you memorized and know, and you just plow through it. So that's the part. So mechanical oscillation. So, you know, mass a half a kilogram, you put 0.5 there. It's just, you know, the numbers are given. The numbers are given, you just plug them in and you just grind through the same stuff we did up there. And this might be 10 cosine 9t, right? So you just plow through undetermined coefficients. You get your yc with the factoring, and then you do your undetermined coefficients. There will be no repetition in this case because it's, right, cosine of 9t. So it's right, it's not going to be repetition. And you kind of want these because generally you don't have repetition, right, for these guys. So, right, these are, and so plus circuits. So the idea is, here I'll write it in blood, know what M, C, K, R, C, L are, so you can plug in, right? That's it. We developed the models in class. We solved models in class. We saw that it's exactly, the solution is exactly what we learned in 3.1 through 3.3. And then what we also learned in 3.5 if you have a driving term on the other end. So there is literally nothing else other than that. And every problem we do would be a repetition of what we did before. So that takes mechanical oscillation and circuits out of the. So there is also, I believe it's a substitution method, and then, or maybe separation of variables, and also someone mentioned about integrating factor and the population problem. Population is another one of the word problems where you plug values into the differential equation that it's given to you. So if you remember, let me just go population. So if you remember that dp over dt is k squared p, I mean, no, what was it? It was we had the AP squared minus BP, I believe. I believe that was the thing. And then we converted it into KP P minus M, where this was your carrying capacity, and K was the proportionality constant, the growth rate. And in this case over here was birth and death. And both of those, right, both of those carried over to I can't remember. Let me just find it. This might be a little bit off. Give me a second. Where was that thing? Yeah, birth minus death. Oh, okay. So birth minus death. Okay, so let me use the same notation as in the book with the alpha and beta and all of that stuff, and I'm gonna rewrite all of these. So birth minus death. So birth minus death. There we go. Times the population, and that worked out to be Kp M minus P. There we go. So that was the population, that was the growth rate of population, and that was your carrying capacity, right? And when you go through the solution for the whole thing, which is what we derived in class, we get that P of t. Now that was MP0 divided by P0 plus M minus P0 times E to the negative kmt. There we go. So that was the solution. P0 was the initial population, and M and K are what we had before. So your population models, again, this problem was solved in class, and the accompanying graph, right, which was like, whee, like that, right? We talked about carrying capacity, especially now the situation we are at with the virus, right? Carrying capacity, that was the limiting factor M. So you can either think about the maximum amount of people that will ever be able to live on Earth, in terms of Earth can sustain up to a certain point, and after that there's no more resources, no more farmable land, no more, right? We are at the peak of the resources for the planet. Or in terms of the coronavirus, you can model the number of deaths, which is the maximum amount of people that can die from the virus, because we know that there are a lot of people that are naturally immune to it, so they are carriers, but the virus doesn't do anything to them. Just like HIV, some people spread HIV around, they have no clue they have it. The others catch it and die very quickly. So since not everyone is the same, right, the virus, disease or whatever could kill, could make sick, and then person gets better, or the person will get it but not even flinch, right? So we know that we have people now that carry COVID-19 and they're asymptomatic, it does nothing to them, but they spread it around, right? Which is why testing is important, right? So we can try and slow down the exposure. But others, right, with pre-existing conditions and so on, right, they catch it and that's it. So that's what the carrying capacity, the limiting value M is, right? Once you take the limit over here, this part will go to 0, and that kills this as well, right? And then you just have P0 cancel P0, and you see that the limiting factor is just M, which is the carrying capacity of the planet, or the maximum amount of computers that can be infected with a certain virus, or humans that can be infected with whatever virus, right? The animals and whatever. So for population problems, you just read the problem and plug in numbers where they belong, right? This is a solution. So technically for the word problem in the population, you are not solving it because the solution is already given. You're just plugging numbers in and working on arithmetics. Can we do an example? An example. Okay, let's see what we can get. All right, so let's pick United States population in 1930. I'll pull that off, or let's go after Second World War. So now 65, whatever. So US population in 1965 was, and I'm just going to get that number on the internet. So US population in 1965. So in 1965 you have the population to be 194.3 million. Right, that's 1965 data. Let's say, and growing at the rate of, let's go at the rate of 1, or let's go 0.9 million per year. let's say. Now, so let me see. So what else do we need? So we have the population in 1965 was so and so, and it's growing at the rate of 0.1 million per year. We need one more point in time because we have two variables. We have a variable k and a variable m, right? So that's the US. Now let's say US population in, I don't know, 1990. So let's go US population in 1990. So I'm getting was 250.1 million. The kids are destroying the house up there. And growing at the rate of, I don't know, 1.3 million. I don't know. I'm just making this number up. I looked up the real population, but I'm just making up 0.9 and 1.3 so we can just plow through this. Okay, so what do we have? Well, we have that the rate, right? The rate is the population minus so now we have to do the formula where you get your K and M, right? So we have I'm very careful which variables to use because I don't want to get 194.3 K and then the carrying capacity of the US minus 194.3, right? So that will be the rate, and the rate was 0.9, and the other rate is 250.1 million times the K, and then carrying capacity minus 250.1 is equal to 1.3. So this is the setup where you are going to get your K and your M, and you just plug them in. That's all it is. So we have our K times M minus 194.3 equals to 0.9 divided by 194.3. That's the first equation. The second equation is K and then M minus 250.1 is equal to 1.3 divided by 250.1. So now we calculate these values. So 0.9 divided by 194.3 is 0.004632, and the other one is 1.3 divided by 250.1 is 0.005198 when you do that. So from the first equation, K is equal to 0.004632 divided by M minus 194.3, and from the second one, K is equal to 0.005198 divided by M minus 250.1. Set them equal to each other because k is equal to k, and you will be able to calculate m, then bring m back and calculate k. So now when you set these two equal to each other, you get 0.004632 divided by m minus 194.3 is equal to 0.05198 divided by m minus 250.1. And you cross multiply, add all of the values, and you will have your m. So 0.004632 m minus, now you multiply that by 250, so we have 0.004632 times 250.1 is going to give you 1.158 equals to 0.005198 on the other side, m minus, and now you have 0.005198. So what I'm doing is I am just cross multiplying, times 194.3 is 1.01. When you know, because it goes 00997, so it's just 01. There we go. So now put all of the m's together, put all of the n's together. I mean the constants together. So move this one here, move this one there. So that's going to be point. I just don't want to think and want to get to this as soon as possible, so I'm just going to use the calculator instead of actually subtracting it in my head. I'm getting negative 0.000566, right, equals to, and the difference over here, since this is a positive, it will be a positive. So, oh, I forgot m. M, and then on this side I'm going to have 1.148. So now I need to divide that. Oh, it's a 0 here. I was trying to figure out why is this wrong. 1 minus 1 is 0. Alright, so now we have this number divided by 0.000566, and that's going to give us 261. So m equals 261.48. Now, this is terrible because it ends up being a negative number. It's supposed to be a positive, so there is a negative minus sign mistake somewhere in the whole thing. It needs to be, you can't have carrying capacity for United States to be negative 260 million, right? So, and this number is wrong, right? Because in terms of because I made up those 0.9 and 1.3 growth rates, right? We already know that in the United States we have 320 million. So, and this over here tells me that we can't have more than 261.5, right? So clearly what I'm doing here is not representing US because I made up 0.9 and 1.3. I don't have those numbers. But I did use correct population for 65 and 1990, so this is, somewhat relevant. And what I'm going to do is I'm going to now plug this back in and calculate K. And you can do that in any of the equations above. So K is equal to 0.004632 divided by 261.48 minus 194.3, and that's going to give you K. Once you have K, plug in into the model, right? So you plug into your P of t is equal to MP0 divided by, right, the whole equation that we had before, and you will be able to start calculating populations. So we have P0, what was that? P0 plus M minus P0 e to the negative MKT, right? So you can plug all of those values in, and you will be able to compute population and so on. Now, if you're asking what is initial population, well, your initial population, P0, is at 1965, because 1965 you're going to set as your t equals 0, which immediately sets your P0 to be, what was our number? 194.3, right? So your P0 will be that. And then you calculated M, which is this. You know what the K is, you know what M is, you know what P0 is, so you have them all, right? And then you can just say, okay, I want to calculate what is the population in year 2000. Well, 2065 is when we started, so that has to be 35, right? If you do that, then the year 2000 would be 35 years later from your initial, right? So you're technically resetting United States, and you're saying, okay, nothing existed prior to 1965, and all of a sudden, switch on, and United States exists from 1965, and the initial population to start going on is 194.3. Now, obviously, numbers that you will get will be off by what they actually are, because again, I made up two numbers, right? And because I made up two numbers, they're going to be a little bit off. But you have the idea of how this is solved. So literally just plug in. We don't have any calculus done in these population problems, right? Because we solved both problems, the basic one and the logistics one, in class when we shoveled those variables and did all of the integration and everything, separation of variables, right? That's what we did. And that's a solution for all word problems. Now it's just a question, what do you plug in and where? So that's what we have. So that's the population problems. Now there were, what do we have, 20 minutes, or actually 10 minutes, but let's see, integrating factor. I have no clue which section that was in. Maybe 1.5? Is it 1.5? I think it's in 1. Trying to find, yes, integrating factor is in 1.5. And okay, so integrating factor, rho of x was e to the integral of p of x dx, if you remember the formula at all. And your differential equation, right, your differential equation was given as a y prime plus p of x y equals to q of x, right? That was the differential equation. So this is what you are remembering for integrating factor. And now when they give you a differential equation, you first have to put it in the form, and then you have to calculate integrating factor and plow through the rest. So I don't know any of these problems. We haven't solved any problems with conditions, so let's find a problem with a condition and do that one. So this one, let's see if 14 is going to work, because they have all of the problems on a pile. So I'm hoping that it will work. And y of 1 is 10. So xy prime minus 3y equals to x cubed. Good. So we divide everywhere by x, so we can get y prime minus 3 over xy equals to x squared, from where we find out that the p of x is negative 3 over x. Right? So now what we are going to do is we're going to do the integral, right, for our integrating factor rho. So I am going to say that rho of x is equal to e raised to the integral of negative 3 over x dx. So rho of x is e to the negative 3 ln x. We don't need the plus c here. Now negative 3 will go in as the exponent of this x. So rho of x becomes e to the ln of 1 over x cubed. And we just get 1 over x cubed as the answer once ln and e cancel because they are inverses of each other. So that was calculation for rho of x, and that is what we need to multiply into our problem up there to make the problem possible, right, to solve. So what I'm going to do is I'm going to copy this one more time, leave some space in between, and then start multiplying this 1 over x cubed everywhere. There we go. Now, this is supposed to compress using the product rule backwards, right? It's supposed to compress into y over x cubed prime, and needs to be equal to 1 over x, right? Because y over x cubed prime is that good. If I have, no, yeah, copy the first, derivative of the second, plus y times y cubed, so which is x to the minus 3. So what is the derivative here? Copy the first, derivative of the second. Derivative of the second is negative 3 negative 3x to the why is this weird? Oh yeah, negative to the fourth. Yeah, it's good, it's good. Because it's this, and then plus copy the second x to the minus 3 times y prime. Yeah, we do have it. See, this thing is here, and yeah, it's working. Good. All right, so you use the product rule backwards to push it into the single derivative there, and once you have it in the as a single derivative, you integrate both sides dx. That would kill the derivative, so you just have y over x cubed, and on the other side you have ln of absolute x plus constant c. So now you have plus c because you are integrating in the problem. Multiply both sides by x cubed, and we're getting y equals x cubed ln x plus cx cubed. Ta-da! So that was integrating factor. It's fairly quick. The only hiccup is, right, pushing the derivative back, right? So you gotta practice that one. I stuttered a little bit, but then I made it work. So much fun. And in this last few minutes, let's dig into emails, see a whole bunch of stuff over here. Oh, I see the eigenvalue problem in one of the emails. No, we haven't covered that yet. So you don't have to worry about that problem. Undetermined coefficients in the email, we did that one. More undetermined coefficients, we did that one. We did the population. Oh, okay. Here is something that looks scary. We might not have time to solve this, but at least we can start it. 8xyy prime is equal to 8y squared plus 9x square root of 5x squared plus y squared. So it looks terrifying, right? And what I'm going to do is divide by 8xy everywhere, because they can't be zeros. They can't be zeros. And that gives me y prime is equal to, are we still on? Because I had, the tablet is starting to behave. It's been streaming 2 hours constantly. So, all right, so we have 8 and 8 cancel, one of the y's, so y over x, plus 9 over 8, x and x cancels, and under the square root, when y goes under the square root, it will pick up the square, so it will be 5x over y squared plus 1. Because what you have is 5x squared plus y squared divided by y squared. That's what you have under the root. When the y goes under, remember 8x was used up in front. So 8x is used up in front and only the y goes under the root. When it goes under the root, it picks up the square and then it creates the term we have below. And at this point, we can do the sub, right? We can say u equals y over x, y equals ux, and the y prime is copy the first derivative of the second plus copy the second derivative of the first. So, and then we plug everything in, right? So y prime is u plus x u prime equals to y over x is u plus 9 over 8 square root of 5u squared plus 1. No, lies. 5 over u, because this is x over y, not y over x. Ha! Caught that mistake immediately. So divide both sides by u. Divide both sides by u. I think my tablet is overheated now. It's really, really hot. And it keeps flickering and shutting off, and the fan is working. It's just going crazy. So we have now u prime so I'm just going to write it x du dx. Right, use the good notation. 5 over u plus 1. There we go. So now we separate variables. So we have du over the square root of 5 over u plus 1 is equal to dx over x. And there is 9/8. Forgot 9/8. And now we just integrate both sides and we're done. Now integrating left hand side, right, is going to be a little bit trickier, but let's see what we can do. Integral of 1 over square root of 5 over u plus 1 du Alright, this one is easy. We want to waste time on this. Just ln absolute x plus c. We're done, right? We just need to work out the left-hand side. So, what do I have here? I have integral of the square root of 1 over 5 over u plus 1. And I have to work this out so I can flip it with a 1. So let me just say that this is 5 over u plus u over u, so that I can actually switch it here. Oh my god, the tablet is just non-responsive at all. It's so slow. U plus 5 over u. And when we flip that, it becomes square root of u over u plus 5 du. So that's what we have. And then we have to use a back sub to solve it. So say g is equal to u plus 5, dg is equal to du, and finally u is equal to g minus 5. We'll need that as well. So when we do the substitution now for g's, it will be the square root of g minus 5 over g dg, and this can be split. Oh, it's a square root. You can't split this. Just Wolfram alpha. Just Wolfram alpha the integral, because I have to go to the next class. You have the procedure. It's a substitution, right? And once we cancel everything and we use the substitution, it works out nicely, and then we just need to deal with calculus 1. So it just needs to deal with this. The rest of the differential equations were done once you separated the variables, right? And once you separated the variables, it was all done. What do you mean 5 over u squared? I'm not sure what the 5 over u squared is, because there is a square root. It's a function composition, so you might have to use by parts. You have to use some kind of witchcraft here. It's not probably this did not work at all. I don't know if it worked or not. So try to play with it's calculus 1 to deal, or maybe calc 2 to deal with this. But our differential equations ended here, right? When you separated variables, and now it's just are you able to integrate? Oh, it was squared. What was squared? Ah, that's a square right there. Now I see. So that's going to be a square right here, and that should fix this. Okay, a square. And that's a square. So that's a square. So those are all squares on u's. And I will have a square and a square. Oh, this is a joke now. That's a square and that's a square. Oh my god. I see, this is how rushed and tired and exhausted and crazy I am because of this stupid situation we're in. And it's just frustrating. So this is the u goes in front. So u goes in front because you have u squared, and you are left with u squared plus 5 raised to the negative 1/2 du, and you are now using basic u sub. Well, we'll use the g sub. U squared plus 5 dg is equal to 2u du. We need to fix the constant there, it becomes 1/2 integral g to the negative 1/2 dg, because this together is a dg. And now you integrate. It's 1/2 g to 1/2 divided by 1/2. They will cancel. You don't need plus c because we have plus c on the other side. So now this becomes a square root of g, which is u squared plus 5. And finally, what was u? U was y over x. So y over x squared plus 5. So now solution. Square root of y over x squared plus 5 is equal to, where is the other one? There it is, 9/8 ln x plus c. 9/8 ln absolute x plus c. And you can't make this much better, or maybe you can. Square both sides, that's y over x squared plus 5 is equal to 9/8 ln absolute x plus c squared. Then you do -5, then you do the square root, and then times x. Holy nightmare. So y is equal to, we have 9/8 ln absolute x plus c squared. We take away 5. Then we take the square root of all of that, and then we multiply it by x. Yeah, I just wanna flex. I hope this would be something that is acceptable. I don't know. It just keeps cutting out. It's so yeah. So these are the problems. Please review all of these. Some of these are longer than what I would like them to be for the test. This substitution problem here, in terms of difficulty, is a joke, but in terms of the length and how long it takes to solve all of this, right, is an issue. So please keep learning and studying the formulas. As I said, don't bank on that you will be able, right, to look up every example and then study it then and try to repeat the steps. Right, learn these concepts not just for the test. No one cares. The test, it's important to learn. This is elementary course, differential equations, for your later courses when you transfer. And if you don't know it, you won't get far once you transfer. So you just need to know these things. All right, so that's it for now. I am sending emails for Microsoft Teams. If you need more, I should be back on online at 4 o'clock to do the virtual office hours. We can try that and see. I did try it already, kind of worked out, but I have to go now because I'm running late for my algebra class. Then I have the family thing, then I have office hours, then I have another class. It's just never ending. I have no time to go and catch up with emails, and it's just, at this point, it's over 1,000 emails. It says 999 plus, because I just don't have time to go into all of that. I'm barely keeping up with the announcements to see what's happening with summer courses and what's happening with fall courses, and is anyone signing up for those, because the situation is that they're not allowing us back into building, and it's just issue. So please look for the announcements, and the next class, which I can also use a little bit to answer some questions on Friday. Planning to have this test on Friday and Saturday, right? Friday and Saturday, and I'm hoping to have it on Canvas. So let's see where that goes. Bye. Announcements on Canvas. Please read that stuff.